I'm Lolim Cho, and I'm going to explain the dielectric properties. So to start with, we'll first talk about the capacitor. A capacitor consists of two metal plates. One is positively charged, while the other one is negatively charged. And therefore, there will be an electric field flowing downwards. And imagine if there is a dielectric material put inside the capacitor, like this one, and the molecules inside the material will be polarized, which means that the positive charges will lean towards the negatively charged metal plates, while the negatively charged of the molecules will lean towards the positively charged metal plates. So there will be a net positively charged at one surface of the material, while on the other surface there will be net negatively charged. So therefore, there will be an internal electric field inside the material from this direction to this direction, pointing upwards. So we can see that the direction of the two electric fields is actually opposite, which means that the electric field, the strength of the electric field of the outside electric field will be decreased by the internal electric field. And the dielectric constant is related to this model because it is about the polarizability of the material, which means that to what extent the molecules inside the material could be polarized, or to what extent there will be an internal electric field formed inside the material. And it is also related to how much energy could be stored inside the dielectric material. So imagine if there is an alternating electric field. When there is an alternating electric field, the charges of the two metal plates would be changing constantly. So the dipoles would need to switch back and forth constantly in order to get aligned with the direction of the electric field. So however, the rotation of the dipoles may not be instantaneous because the charge carriers have mass. So therefore, the electric field has to do work in order to move the molecules. And so the rotation of the dipoles could lag behind the changing of the electric field. And when there is a lag behind, it causes friction and heat loss. And therefore, therefore the electromagnetic energy would loss in form of heat energy. And the rate of the heat loss is measured by or is related to the dielectric loss factor. And here comes to the dielectric properties of timber. And some scholars conduct experiments to measure the dielectric properties of three kinds of timber at microwave frequency. And parts of the results are summarized in these two figures. You can see that the dielectric constant is actually positively correlated with the moisture content. So we can see that the dielectric constant value increases gradually with the increase in moisture content, while on the other hand, the dielectric loss factor is also positively correlated with the moisture content. And you can see the trend from that figure. So generally, we can say that when the moisture content is increased, the dielectric constant and the dielectric loss factor will also be increased. And this relationship could be explained by the difference of dielectric properties between water and timber. It is pointed out that both the dielectric constant and the loss factor of water is much greater or higher than that of the timber. So it is reasonable to observe an increasing trend of the dielectric properties of timber when the moisture content is increasing. And moreover, when the moisture content of timber is higher, water molecule tends to penetrate into the cellulose, and which will weaken the binding force of the dipoles inside the timber. So the dipoles could deplate to a larger extent, which means that the dipole polarization will be greater, and therefore the dielectric properties of timber will be more pronounced. So here comes to the dielectric properties of glasses, and we have gathered some information about the dielectric relationship between the dielectric constant and temperature of silica glass at frequency of 9.4 gigahertz. And in order to observe some changes, we make a table based on the data that we have obtained. And here we can find that the dielectric constant of silica glass actually is positively correlated with the temperature, which means that the dielectric constant will increase with the increase in temperature. However, actually the increase of value is not very significant, but still there is a trend. And this trend could be explained by the following reasons. It is suggested that when the temperature is increased, the mobility of cation ion will also be increased, and therefore the polarizability of ions will be increased. That means that the ion polarization inside the glasses will be greater, and therefore the dielectric constant of glasses of the silica glass will also be increased. So we have also gathered data from several reports, and we find that actually the dielectric properties of glasses vary significantly with their composition, and the results are shown in this table, and so we can see that the values vary quite a lot, and this the difference between them could be explained by the difference of the polarizability of different ions. For example, it's pointed out that the oxygen is the most easily polarizable ion in glasses is oxygen. So it contributes to the difference between the values of the dielectric properties between different gases. So we have mentioned the different affecting factors between timber and glasses, and for example, timber is majorly affected by the temperature, while the glasses are majorly affected by the temperature. So we can see that a fair comparison is actually quite difficult to conduct. However, we would like to do a comparison, and we would like to make it under an ambient environment, which means that it will be conducted at the room temperature, and the relative humidity will be 55%, and it's a microwave frequency. And for timber, when the relative humidity is 55%, the moisture content is suggested to be at 10%. So we will use the value of timber with moisture content of 10%. So we can see that generally the glasses have a higher dielectric constant than timber, which means that the molecules inside glasses would likely to polarize more than that of the timber, and therefore the glasses could store more energy when a microwave pass through it. And on the other hand, glasses generally have a lower dielectric loss factor than that of the timber, which means that when the microwave pass through glasses, less electromagnetic energy will be lost in form of heat due to the lag between the rotation of the dipoles and the changing of the microwave, the changing of the frequency of the microwave. And so here this is our comparison, and that's all.